also unmuted.
Okay, and that's not going to be a problem with the mic here.
Yeah, that's what makes it more.
And the lapel mic on at all times, right?
Oh, actually, and there are people listening.
Right, keep it on at all times and keep it unmuted.
Unmuted. Okay, cool.
And then you can just.
We might tap the microphone gently just to see if it works.
Sounds good. Cool, cool.
See her screen. Just share that.
Yep.
Okay. And I see part of your screen. So now we will need to pull your slideshow.
What?
I need to pull it up into slideshow.
Yep.
These questions in here.
Okay, and then so I need to go back to Zoom and share the PowerPoint.
Yes.
Okay. Oh, boy, it's having to think about it really.
So the one thing that
Now I've got,
You can Alt Tab or
Yeah.
Control up. And select Zoom and then share the screen, your entire screen. That'd be great.
share the other screen, not Microsoft Power.
PowerPoint would be okay. Let's try it.
That's what I've used for normal Zoom meetings, so.
Sure. Okay, I can see the screen. And so just moving as you're.
What was that, Brian? Quick, you repeated.
Just making sure that the slides are able to move in the room.
So she's trying to slide. Okay, okay.
So what we were gonna try to do tonight.
Okay,
Are they gonna try I think it's open here.
If you remember which pointer slide controller. Let's go ahead and use this. Let's start with. Okay, try and hit next.
I don't think it's red.
Let's try the other one. We have like just a couple.
we can live without pointer.
Cool.
Let's just leave it. I can use my laptop keyboard. It's not a problem. That would be great. I will try to describe it so people online can tell what I'm gesturing at. That's the green button. Okay.
Let me quickly give it my number. N is 0, 552 0 2 2 0. But I want to go ahead and get started.
Yep. All right, bye, John.
So I'll go ahead and get started. This is one of the few in-person moving events for us. Seems like people haven't adjusted this time or I did want to say a little bit about Professor Mills. We went undergraduate at Harvard. She got her PhD at Santa Barbara, working on CDF data, and she moved to Harvard, where she worked on some of the very early LHC data, and then 2016 she obtained a joint appointment, became chairman and University of Illinois Chicago. So without further ado, I'm going to go ahead and let Professor Parker talk about the Genesis, the big bosons, and what's next. So thank you. Let's get
Thank you. Great pleasure to be here in person in particular. It's my first in-person talk like this in a few years now. And thanks for letting me postpone for 2 weeks, although I see you arranged already. Anyway, have the snow. So very, very brief overview of the talk. I have a few parts. Talk about what Higgs boson is and why we study it. Talk about a new measure that I've done in the Higgs W final state and why a path that might first glance look suboptimal. The answer to that question has to do with baryogenesis, what it is, and we'll talk about what it has to do with Higgs bosons. Then I'll make a historical digression, and finally talk about silicon particle tracking detectors for the high luminosity LHC. So my first couple of slides are a little bit tongue-in-cheek. There's the standard model from the point of view. We have a bunch of questions, and they're all basically the same. We have the up and down quark of ordinary matter, the electron that makes up along with those the atoms of ordinary matter, neutrinos, but these are all just leptons. Neutrinos are neutral. We have the force carriers that are the gauge bosons. You can write down a Lagrangian on a coffee cup. The experimentalist's view is that it is very straightforward. If you want to do calculation, we run a Monte Carlo, we run a numerical calculation and a Monte Carlo simulation for how things look at a detector. And the world is just full of nice Feynman diagrams. Again, I say a little bit tongue-in-cheek. If you're an experimentalist, each one of these particles has its own distinct personality and quirks, and you have your own personal relationship with that particle after enough years in the field. And mine is up, down, charm, strange. These make jets. It's actually a new paper where we can really start to tell charm jets apart best, but that's different. Top, heavy, distinctive decay to a W boson and a quark that will be relevant later in the talk. Bottom quarks make taggable jets, and jets are sprays particles in the detector as a consequence of strong interaction. Electrons and muons, very clearly identifiable detector because they don't interact strongly. Taus, not so easy, heavy enough to decay. Neutrinos, a whole topic of a whole subfield of experimental physics, and they're right, are just missing transverse energy. Z and W boson we like these. They often decay to charged leptons and neutrinos. This is very easy to identify in the detector, and they'll feature exclusively in the measurements, and so I'll talk about. Photon, good energy resolution, nice for the Higgs boson mass. Gluons, LHC is a gluon factory, and that is mostly how we will make the particles that we are talking about. So what is the Higgs? It is field, and I said Higgs instead of Higgs boson because there's kind of three aspects to it. There is the Higgs field, complex scalar SU2 doublet, 4-degree freedom. There is a mechanism. The ground state of this field, illustrated in the cartoon 2D version, the classic potential. The ground state of the field is actually not a condition of zero field, which is easy to say, and if you actually think about it, is kind of odd because imagine if the electromagnetic field were not zero ground state. There'd be a preferred direction in the Earth. And so it's not zero fields, so there's no direction. Interactions with this become the mass of fundamental particles. And 3 degrees of freedom that are being become a longitude 3 degrees of the freedom and become the longitudinal polarization of the two W's and Z. And therefore their masses is, and thirdly, the Higgs is a particle that represents the excitation field. This is the reigning degree of freedom. It's a scalar. We label it with a capital A, lowercase h. I will pretty exclusively use the lowercase h because the capital H is reserved for heavy Higgs bosons. It interacts with every particle that it gives mass to, including the fermions. And I want to make a clear distinction between talking about a Higgs boson and the standard model Higgs boson. Once you're talking about the model Higgs boson, predictions get very specific. This is one and only one physical particle, and it gives mass to all of the other particles of the standard model, including gauge bosons, including the fermions. Leptons, quarks, everything universal with the interact determined only by the mass of the Higgs, the other particle, and the vacuum expectation value, which is that ground state of the field. That's it. It's very constraining, which makes experimentalists happy because we have something very well controlled that we can go try to break. And so this is the Higgs branching fraction to give you an idea of the landscape. This is part of a specific set of predictions. Then finally, a third distinct question from what is this model Higgs boson is, what is the bit 125 GeV? So this is now shockingly 10 years ago that we had discovery into 2012 of a Higgs boson. This is an experimental question. So one of the very class plus, it's at 13 GeV, so it postdates the discovery, although it's a little bit older. And I want to use this to introduce briefly the visual language of particle experiments. We have this is a great text case for it. I like to poke fun at the ZZ to 4 lepton that it's too easy. Because each of you, because you start out with the decay to 2 Z bonds. That seems like a small slice of the pie to have. And then 3% of those bosons decay to a pair of charged leptons. Then you have 4 clearly reconstructed objects in the detector, and you reconstruct the invariant mass. And that corresponds to the mass of the particle. And so you see the continuum ZZ action here, including the resonance where 4 leptons coming directly from 1E. It's actually ZZC star, one of them shell. And then you have a continuum background in green, and then you have your sin red. So what we have is a stacked histogram showing the backgrounds we've predicted, showing sin. Then we compare that to what we see in the data, which is represented by a bunch of points that have errors. And we compare those and decide if they agree. And so in this case, you can see very clearly that if we did not include a Higgs boson at 125 GeV, our data would not be predicted by the model. That's how that is part of in one channel of how we were able to discover it. But the Higgs boson is not just a ZZ to 4 leptons. Because of where the mass happened to land at 125 GeV. So this isn't, so what I showed earlier is a slice, that pie chart is a slice through this diagram, which is itself a function of the Higgs boson. And this is what the landscape looked like. This full mass range is possible, theoretically, for the standard model Higgs boson. And that was where we're when this was first predicted. So you can understand why I went to go work on Higgs to WW in 2011. I had experience reconstructing final states with 1 and 2 bosons. So this was a pretty clear place again with an excellent physics motivation. I managed to get in just in time to have a furrow seat to the discovery in 2012, which and the following rapid progress on characterizing the new particle, which was really a once in a lifetime, hopefully not just once in a lifetime, but certainly a unique experience. But the point in showing this plot is to show that because of where we happen to land in the mass spectrum, we have a really broad experimental program for how to characterize this particle. Sometimes we talk about big final states, BB, WW, ZZZ, diphotons, and tau. Diphotons is down here, but because of that great ability to measure them in the detector is a very important decay mode. So we have many final states, and we all have many production modes. So we have all the combinatorics of all of this, which will be very clear in the plot I'll show after this slide. But first I have to introduce the second half of the combinatorics. Now, what the LHC is essentially colliding protons such high energies that we're basically colliding a bag of quarks and gluons, colliding bags of quarks and gluons. The light quarks and the proton are very, very, very light. The gluon is massless. This seems like a miserable way to make a particle that couples to mass. But you can have intervening heavy particles. And so that's what characterizes all of the Higgs production modes at the Large Hadron Collider. Here, the gluon fusion. So these are our most common modes. And in greatest to cross-section mode, these span about 2 orders of magnitude. Gluon fusion, where you have an intermediating loop of heavy quarks that let 2 gluons connect to a Higgs boson. Associated production, VH, will feature prominently in this talk. The V, either a W or E. And you have a QQ bar mediated by that W or Z. And then the Z lands in the final state, in addition to this boson. This is very nice because that WW can give you a distinctive leptonic experimental signature. That's the third in a row. The second most common one is vector boson fusion, which is a different way for the light quarks to produce a Higgs boson mediated by the heavy gauge boson. And finally, TTH, which is sort of like you in the triangle in the gluon fusion, open the triangle in the gluon fusion diagram, and you produce those 2 top quarks on shell in addition to the Higgs boson. It's a very low cross section, but quite a spectacular signature. And we have, and the LHC experiment, Atlas and CMMS, have gone through this in great detail. At this point, we have covered almost every combination of production and final states. And we big combination plots like this that are kind of brain-meltingly complex. I mean, this is a lot of numbers to digest. We make a lot of plot this. So let me briefly explain what is happening here. The line, so this is the x-axis is the cross times branching ratio normalized to the model prediction. So the line at 1 represents the theoretical prediction. If one of these experimental points lies on the line, it matches under model prediction. The statistical uncertainty is the yellow error bar. So you can see if you have a particularly rare combination of action and decay, like a VHZ, you have a very large statistical uncertainty. But otherwise, see the blue bars are becoming done, the systematic uncertainties. And overall, the message of this plot is you've covered everything really well. And the best measurements are approaching 10%. It's only going to get better. And I do still hold out hope personally that we will see some cracks in the foundation. But for the most part, this is so far disappointingly conforming to standard model expectations. I've shown that this plot. There's going to be a new CMS combination in this which my measurement that I will be part of. I'm going to jump back briefly to talk about how we produce these. I mentioned large hadron collider, which is where we get these which calls protons, which is where we get the quarks and gluons to make the Higgs bosons. It has been pointed out to me since I DMS that when I took this picture, I was on Atlas, and Atlas is in the picture, and this is off over there in France. And so I have on my to-do list that I need to go back to the top of the Jura and take a more appropriate picture. It's been a little difficult to get back there these days. But I love how there's the mountains and everything, the scale of the CMS detector is not as large as the ring. It is still quite a beast. This is meters across, tens of meters tall. Overall diameter 15 meters. It's dominated into volume by the muon detectors that sit outside of every, and the return yoke for the magnet the solenoid magnet that forms a particle spectrometer out of this. Inside of that is a calorimeter. There's a hadronic and electromagnetic magnetometer. These are what measure the hadronic component of jets, and as part of why we can measure photons so well. And all the way here in the middle that you can really see in the yellow at the very heart of the detector is the pixel tracking spectrometer, which is the part that I'm working on upgrading for the high luminosity LHC. So we're going to zoom in a little bit here, show how the muons traverse the entire detector. So this is the center of the detector. So now we're just taking a transverse slice of the detector, of the CMS detector. We have a silicon tracker very schematically rented here, and it shows things how like the photon doesn't even need tracks because it's not charged. But we see it in the electromagnetic calorimeter. Electrons are the same, but they have a track and electromagnetic shower. Hadrons make messier showers, but we can distinguish them to some extent. Ones make are charged hadrons and make tracks. Others are neutral hadrons like neutron track and do not make tracks. And only muons persist all the way muon spectrometer. And finally, neutrinos we only can infer through by invoking the conservation of momentum and noticing that the event is in one direction. The missing transverse momentum, which has been a gradual transition for all from calling it missing transverse energy, getting back to it was only measured in the calorimeter. But now I'm going to zoom all the way in the very center point of that detector, talk about how the pixels in the detector is the particle construction. So what this shows is colored lines or tracks. At the center is the interaction to the detector, and you can see sets of tracks coming away from the vex. You can see where the two sets of tracks each cross at a point that is distinct from the main interaction vertex. And I want to bring out the contrast in scales of the detector that's 15 meters in diameter and the tens of micron scale that we're looking at in this figure. And so this requires very precise precision measurement, precision-based measurement. And most classically, we talk about the uses in terms of displaced vertices are a signal of heavy flavor, particularly hadrons coming from bottom or charm quarks, which travel a little ways in the detector before decay. We identify jets from them and also reject leptons that come from their decays, which is particularly relevant if you are wanting to make experiment identified leptons and W Z boson decays. You wanted to distinguish between these, which are far greater number, and ones coming from the W and Z boson. And the ones coming from the W and the W Z boson will be consistent with the origin. Then we can start to dig in a little bit the Higgs WW signature. So you saw in the plot versus mass, if you don't know where the Higgs boson mass is, this is the channel you want on. If you think Higgs boson is above 40 or so GeV. This is an appealing channel because of the large branching ratio. The B bosons themselves are not what we reconstruct. Each W boson decays into a QQ bar or so the big pies get split up. And until recently, the main place was the dilepton channel because of the best background, that has the best signal to background. So even though that's the tiniest slice of the pie, that was the channel that contributed to the Higgs discovery. And so this was actually what I worked on there. It's the best of the background, but relies on the gluon fusion, the highest production crossing. With more data, the V production mode becomes accessible. And I got interested in going after a bigger slice of K fraction pi. So this is the figure that I've been working on. We have a Z bond decaying to two charged leptons, Higgs boson to two W bosons, one of which is off shell. One decays to quarks, which become the detector. One decays to a lepton and neutrino. And then there's other jet recoil off of it. It's the LHC, and the LHC always makes extra jets. And the idea, part of the idea behind this was to balance the low production cross section with the higher ratio to L nu Q Q Q. One mental note is that we measure the transverse versus distinguished against background. This is like the invariant mass, which is what I showed for the ZZ channel, but it omits the Z direction of the momentum because we don't know that for the neutrinos because we don't directly reconstruct them. And the kind of goofy, but actually surprisingly accurate way to describe it is that it's that down to calculate the invariant mass. You discovered missing some of the information, but you were running out of time, so you decided to calculate it anyways and see if it worked. And you find that it actually does distinguish between, it does have a kinematic edge, and you can use it to distinguish your signal and background, which you can see in our plots. Particularly in the Morjet channel where we reconstruct works from the W, the figure on the right. The signal, which has been blown up for virility here, it's in the red line, peaks towards low transverse mass, which is what's on our x-axis here, compared to the dominant background from W production, which is in the yellow, which peaks towards higher transverse mass. So it doesn't give this sharp peak the way we do with a mask, but you can still use it to distinguish against the background. We also include one jet signal region to capture the signal event where we can't reconstruct both quarks because one of them doesn't have enough momentum. And for interest, a picture from one of the other more sensitive, important ones. We do a combination of the 3, 4, and left measure, 2, 3, and 4 left measurements. So including ours along with Z and W plus Higgs WW production, where the W decay L nu. And so these are our. This is the same kind of figure I showed earlier, where unit 1 represents the standard model. The two most precise channels that are driving the precision of the combination are what are called WH3L and ZH4L. These are the fully electronic signatures. Here's ours. We're contributing to the combination. It has the error bar of the 4, but it was just the very first version of this measurement. So we have lots of plans to improve it. We're improving our understanding of backgrounds. We haven't even begun to apply some of the modern data analysis and machine learning techniques to it with a complicated channel state like this. I think should be a quite tractable problem for that. But actually, the reason why I wanted to go this Z signature is that you can imagine that you have another particle that decays to a Higgs Z boson, and that lets you do a resonance search for a new Higgs boson. Why do we want to look for new Higgs bosons? Because it can help solve baryogenesis, which is one of the most important problems the LHC can solve that almost nobody ever talks about. So to introduce the problem, the Big Bang was matter antimatter symmetric. So really everything should have just re-annihilated immediately, but it didn't, which means that we are missing a law of nature because the universe exists. The Sakharov conditions describe the conditions for this to happen. We need baryon number violation, interactions out of thermal equilibrium, and C and CP violation. It turns out that we cannot achieve this in the standard model, but the problem is where you might immediately expect it to be. But with a nice checklist we go through. Baryon number violation. This is the physical mechanism to the number of baryons. Surprisingly, this is the easy part. And it's a non-perturbative solution to the standard model equation called Celeron, which I may or may not pronounce correctly. Interactions out of thermal equilibrium to drive the transition. The Big Bang actually in thermal equilibrium. So we need a first phase transition in order to have some phase boundary that particles can scatter off of. And this is the same kind of phase transition water boiling is. Unfortunately for us, with the Higgs mass at 125 GeV, the electroweak phase transition, which is the transition from the Higgs boson being the Higgs boson field being effective electric to having to pick a ground state. That same electroweak symmetry breaking that gives the W boson's mass It turns out that for our Higgs boson that we have in our universe, the electron phase transition is in order. Finally, C and CP violation. After we know there is CP violation in the standard model. This is measured and characterized in great detail, but it is illustrated by the combined figure showing results. The triangle was flat, there would be no CP violation, but the triangle is not flat, so there is CP violation characterized by the angles in the triangle. What we have is orders of magnitude below what's needed. So it turns out that an extended Higgs boson sector can allow a first order phase transition and provide new opportunities for CP violation. Also, additional Higgs bosons appear in many plausible models for new physics. Supersymmetry is most obvious, but not the only example. And this is a semis motivation. Nature seems to like copies of things, like the generations of leptons and quarks. So why not have more Higgs bosons if we've got one? Framework interpretation that we'll use is the Higgs doublet model. It's a workhorse of BSM Higgs physics. It's as simple in some sense as adding a second to doublet to the standard model. But we don't need more degrees of freedom because the W and Z bosons already have mass. So we get four new particles, four new physical states for the price of one complex scalar doublet field. And this gives a two neutral CPE scalars, charge scalar, and a neutral pseudoscalar. These get categorized as type 1, 2, 3, or 4 based on how they interact with the standard model. This is notably because that label will show up in inputs. And this model is compatible with electroweak baryogenesis. So I got very excited to potentially go for new Higgs bosons decaying to WW directly or to ZHWW. Problem with this is that we're doing too good of a job with measurements of the existing Higgs boson. And if you talk additional Higgs bosons, part of what makes them Higgs bosons, they can potentially share in the role of electroweak symmetry breaking along with observed. Which, in the con of that, is we can use measurements of the existing Higgs boson, place actually quite strong constraints on what additional ones might look like. And these are draw plots, but a lot of the message is in the X and Y axes. We parameterize these by tangent beta, which is the ratio of expectation values. What that means in practice, our Y-axis, as you go to high tangent beta, you have enhanced couplings to down type phons like BB bar, tau, not TT bar, that's the typo. You also have cosine beta minus alpha. Alpha, the angle of rotation, diagonalizing mass matrices. What this actually means in practice, if this is zero, you have a standard model like Higgs. If it goes towards -1, we have a more standard model like heavy Higgs. And the constraints a little bit based on what you assume about the couplings to the different standard particles, but the core message is pretty clear. The search in the space remaining, the options are pretty constrained, and the new Higgs bosons cannot really look like the standard model Higgs boson, and so I was all to go look for a new Higgs boson using my WWW signature. It turned out that was a bad plan in most models. The blue line for WW here, and this is all back in 2015. This was pretty clear. This is not the place to go look for a new heavy Higgs boson. The branching ratio is pretty small, and compared to BB bar or TT bar, it's a little bit dependent on the details of the model. But one of the things to pick up on is that once you get above twice the top quark mass, top and top there starts to really zoom up all of your branching ratio. That's a big fraction of your decays as soon as it's possible, because still a Higgs boson, and it still pulls proportional to mass. So pragmatically, what this is us is that we are in a regime of alignment and or decoupling. Not going to talk about decoupling because that means the new particles are very massive and we can't look for them anyways. Alignment means specifically that Higgs to vector bosons and Higgs to WZ and to a lesser extent Higgs to ZH are suppressed. What's left? BB bar, TT bar, and cascade decays, where you have a Z boson and one of two new neutral Higgs bosons decays to the one plus a Z boson. So you get to go look for two new particles. Because even a production of the standard model Higgs and a Z is not very promising into these scenarios. So you can take the direct approach and say, well, I'm just going to go look for TT bar. And that seems like a great plan because you're not to look for a smaller, if this is going to be your largest section, directly producing just by gluon fusion the same way as the 125 GeV boson. The problem with this is that HC makes a lot of top quarks, the same initial state and the same final state, and we get his interference. And this is a slight old pair of plots, but I like to show it because it shows very clearly what happens between signal and background. Get interference. Instead of a nice hunt, you have to hunt for a wiggle. And you have to hunt for a very small wiggle. This is one of the most sensitive channels in this analysis that has been done on, and which I find personally very, very impressive. Look for this little teeny red wiggle compared to these data points and this background. But it's able to make some interesting limits. What this is doing is making exclusion relatively sensitive to the scalar mass at very low beta, meaning that this prefers both the up-type ferns, including the top quark. The other approach you take, because it'll be a little easier to access because the particles are lower in mass. And this is a cascade decay I was talking about. You go search for two new particles, look for the lighter of the two new Higgs supposed to decay to a B bar pair. And these are just stacked plots in the background, mostly ZZ plus B bar with a bit of TT bar. And the signal starts to smear out as you get to higher masses. Do a nice trick because you can look at so you have a cascade decay. You have two resonance masses to look for. You have the lighter one that decays to the pair of V jets, and the one the heavier particle which decays to the Z plus the other Higgs. So you have a 4 invariant mass, and these are correlated through the jet energy scale. And so you can look for nice two-dimensional bumps like this a lot than if you just tried to measure the one-dimensional bump, which with these two projections on the side. I show this Plummet plot because I think it's a nice illustration of how kinds of searches are interpreted. This is mass of. So you can look for A to H or H to ZA with the same signature, which is convenient. We have the mass of the pseudoscalar on the x-axis, the mass of the scalar on the y-axis. And here we have to pinpoint in the HDM parameter space and scan the masses. And on the right-hand scan the parameter space and look at a particular point pick a particular point on the mass point. So the star is the same in both of these. It is the same point in both of these diagrams, which I find helpful for visualizing exactly what's going on here. And you can see that we hit kinematic limits above about 600 GeV. We are most in kind of a middle of the road tan data, because this is decaying. This is something that's produced more strongly for lower tangent beta, but decay mode prefers higher tangent beta. And we're sitting right on the element limit, i.e. a standard model like light Higgs boson for the parameter space. So my idea, and not just my idea, but the thing that I'm doing next is looking for an AZH cascade where the lighter quote of the two Higgs bosons decays to T bar. This takes advantage of the preference for the cascade decay in the remaining space two Higgs doublet models, and advantage of the fact that the TT signature takes up a large fraction of the branching ratio in the high states. You will notice that this outermost part of the signature is same thing as same thing as we're already measuring. And all you have to do is add two XY jets that are because quarks each K to a top quark. The top quarks each K to a W boson and a B quark. It is actually so far looking like it's going to be smaller than the Higgs to WW analysis, higher mass. You're really just dominated by TZ production. Some phenomenologists have looked into this, and their work suggests that this will actually already give us evidence or interesting limit in run 3, which starts this calendar year. So this is scanning the mass of the pseudoscalar and tangent beta on the y-axis again, showing that we don't reach very high tangent beta, but depends on how close the alignment limit. The mass limits start at twice the top quark mass, and then we hit some kinematics, but we will be able to push those kinematic limits if we take more data. So I think, in my opinion, that is one of our best shots really seeing new physics, the LHC. But I think, to me, it's pretty clear that the new physics is not going to be in the low-hanging fruit. If we will find new physics at the LHC, which I do hope we do, it's either going to be a small signal with a large background, weakly coupled, like the things I'm looking for, or some novel signature that we haven't thought of yet. An example of this is a thing we have thought of and tried is searching for very long-lived particles which travel out into the detector and then decay, and aren't even necessarily synchronized with the beam. But we know there are reasons for new physics to exist. All the questions are still there, but we need to change our mindset. The story of particle for the last 40 years has been a relentless triumph of the model, with just a few asterisks, such neutrino oscillations and the torque mass. But this wasn't, if you go far enough back in history, this wasn't always the case. In the 20th century, it could have looked to you like we knew everything about subatomic particles. We had the proton, the electron, neutrino, and the photon. We could explain electromagnetism. We could do nuclearics. And it seemed like a fairly complete, consistent system. But started to be cracks in the facade. Probably the discovery of the muon, leading to the famous quote, "Who ordered that?" There was initial confusion exactly it was. People thinking, oh, this is the this is a mesotron, the particle that transmits nuclear force. But when we found it's just a heavy electron, that became a bridge to something else. And literally strange things started happening. We found strange quark particles in cosmic rays. C.S. Wu discovered parity violation in nuclear, showing that we didn't understand everything about the laws of physics. We got a partial answer from the quartal in the 1960s. 1964 discovery of the J and psi introduced yet another charm quark and quantum number. There was an explosion of work. We codified the standard model in the late 70s. This gave us the W and Z bosons, top quark boson was all predicted, and we had a map. We knew which thing at all times. Most times we knew which thing next. And the challenge was to build the experiments that could achieve it. And so these were landmark experimental achievements, but few surprises, culminating with the discovery of the Higgs boson. I know some exceptions. I don't doubt.
Why don't we hold this question?
I am also deliberately trying to be provocative. We are sailing off the edge of the map. But we do know have some guiding stars. We know generally the direction we need to date. I talked about one of the motivations, baryogenesis. I'm sure in other particle physics talks, you've seen arguments for the hierarchy problem, explanations that dark matter exists, but we don't know what it is. Gravity, a whole nother thing to try to bring in the world of particle physics. Sorry about that. And the next step we're able to take to try to address this is the high luminosity LC. This is actually the updated schedule. It unfortunately got 1 year into the future. But this is the very beginning. This is run 1 where we discovered the Higgs boson. This is run 2, which is finished. We're just wrapping up shutdown 2. We're here in 2022. We're going to have run 3 imminently. And then after long shutdown 3 in 2027, we're going to over that long shutdown, we're going to gear up the high luminosity LHC starting in 2027. So LHC is going to, if you thought you knew pile up, LHC is going to really open the fire hose. And we're going to see 4,000 inverse femtobarns. So to give you a reference for how much 4,000 inverse femtobarns is, we discovered the Higgs boson with 30. And the price of all this data is going to be 100 interactions per bunch crossing. So this is kind of an artist's interpretation of what that's going to like. And we're going to have a lot of X. And so we need a really, really good tracker to point back to those vertices to make sure that we can reconstruct all those B jets and discriminate against non-leptons and all the rest. So I'm going to give one pedagogical slide on how the silicon detector we use work. It is a single crystal of silicon, so it's a little plate of silicon that operates has segmented electrodes and operates as a set of reverse bias PN junctions. The reverse bias, that electric field, I'll refer to as the high voltage. Sweep any thermally produced electron hole pairs. When you have an ionizing particle go through the detector, it produces electron hole pairs that are promptly swept apart by the field applied. And these induce signal on the implanted electrodes. And then what we do is photos on the next slide. When we have layers of these little plates, build up cylinders and disks out of them so that the particle passes through multiple layers. And we combine, on each layer, we combine multiple pixels. And then I'll have different amounts of charge depleted in them, depending on how close the track was. And we use the charge information to build a space, and we stack those space points together into hit. And that's what we build the tracks out of, which is how we get B jets and all the rest. There's on-chip electronics and offline reconstruction to read this out, amplify the signal, apply a threshold. All the processing that can be combined into clusters is to date handled offline and software. And one measurement we'll talk about is how we comparing the cluster position estimated to measured, or observed to measured. But first, some nice pictures of silicon detectors. This is CMS. So we have outer tracker barrel and module. So this is silicon. This is our current pixel detector, the phase 1, and we actually to UIC just in time to help finish up the testing. They were desperate enough for manpower after the students left that they put new assistant professors to work. And I wrote my first funding proposal sitting in the silicon detector lab. But that 3 disks is dwarfed by what we're supposed to build by 2027. The responsibility is, so this is a one curve of the detector. The beam axis runs diagonal along the page here. Z equals 0 is sliced down the middle. So this is one quarter of the detector. The US is going to build 2 big sets of disks called the forward pixels. And where I've been working on this is at the Free Lab test facility. And so this is a collaboration with your colleagues, John and Steve. The very basic picture of the test beam is what we want to know is how well if there is a particle there, how often we get the hit. If we get hit, how well do we measure position? This seems really simple, and it is the hardest thing I've ever done in my career, is to do these measurements. Telescope, which provides tracks, that's our information, if you will, because we know a particle is there because we measured. So this is where we place our device in the red box. We have measurement plane, well understood measurement planes on either side of it. This lets us point a track inwards towards the device under test. This is referred to as the telescope. Here's an actual picture of it. This is repurposed spares from earlier iterations of the detector. So we have 6 silicon strip planes. They each have us one dimension, so we put them in pairs, so we can measure, get a two-dimensional base point. We've got some pixels. We've got a readout. We've got a cold box in the middle of the week. This is the cold box is about 1 foot by 2 foot by a few inches. Keep the inside of it at minus 30 C in a nitrogen atmosphere. Operate irradiated sensors. And the reason, the main focus of testing is the radiation ability of these sensors, because we're going to put them in the middle of those tracks, in the middle of the detector. And the charged particle tracks from the LHC sequence, adding up over the years, damage the detector. There is displacement damage, is actually physical damage to the silicon lattice from collisions with particles. There's ionizing dose of the readout chip. We are mostly interested in testing first of these at the moment, although the second one can make life very challenging. Readout chip is not working well. We have been doing some of this work at a new Fermilab facility called Radiation Test Area. This was commissioned a little over a year. It draws off the linear accelerator beam line, which gives us 400 MeV protons. So we have the devices in the beam. So we have the sensors themselves. You can actually see the sensors, one in the front. They're mounted onto green circuit boards. We wire them to the readout. We stack them in the beam. They're at an angle to provide us at an angle so that we can get more volume of the sensor to a narrower beam. And we send an order of 10 to the 17 protons through the detector. So we simulate in days what will take us at the LHC. So I will highlight actually that this is the design of Steve and Charlie and made in the machine shop here. And it has worked pretty well. A little bit to some actually rather hot off the presses is test beam analysis results from irradiated sensors. This is a sensor that was irradiated to about a third, give or take, of the HLC fluence. And I'm honored to work with a really great student postdoc, so I've tried to credit them at the bottom of the slide. I've not been the one to make the plot. And so we see here, this is what the old box is kind of like a clamshell. And so when you open up the clamshell, you see the sensor, which is the shiny silver thing, mounted on the circuit board, connected to another circuit board to kind of fan things out to the readout. And this is a pretty small target, 1 by 2 centimeters squared. And we send the beam distinct from the irradiation beam through the sensor. And we're only looking at a third sensor. The plot sort of looks like this because it's adaptable to different sensor sizes and shapes and pixel sizes and shapes. You kind of see the fuzzy edge here because this is the beam spot. What you're looking at is a map of the columns. So every speck on that plot is a pixel. And in hardware, boring are good. The fact that this plot is uniformly yellow tells us that we're running really efficiently. Telescope pointing resolution is about 5 microns. So we can actually resolve details inside the 20 by 100 micron squared pixel if we overlay all the pixels. So this is such an overlay. We have the inefficiency at the corners because this is a pixel sensor design called a 3D pixel, where instead of the electrodes on the top, like the picture I showed you earlier, the electrodes that shape the electric field actually go down into the silicon. And so the electric field is being along the silicon instead of down the silicon. This is expected to be more radiation tolerant. But the price of that is that you see some inefficiency where these columns are. if you're at normal incidence where you're shooting the particles straight into the detector. One of the things that's interesting with the radiated sensors is seeing how they were to increase bias voltage. Because of the lattice damping, it's harder and harder to actually sweep out all the charge carriers from the region. By applying more bias voltage, we can increase the effective area of the sensor called depletion engine. You can see that happening in this charge plot. When a magenta plot is at 10 volts, and we scale through 100 volts, going kind of through the rail here, and you can see that this is the amount of charge we quote unquote collect in electrons, and you see that we see more and more charge as we increase the bias voltage. So that tells us that we are increasing the depletion region. And correspondingly, you can see that this becomes, once you get to 80 volts, you're over 99% efficient with this particular sensor. One note is that we put it at an angle so that we're not straight down on those electrodes, and we are 100% efficient with the full sensor. Finally, the position resolution, which is one of the key, which is how we're going to get from these little devices all the way up to physics. The residual is the distance between the position of the extrapolated track and the actual hidden vector. And the pixels that we're looking at are 100 by 25 microns, so they're rectangular. And you can see that in the resolution, that it's a little wider in the long dimension, and it's 10 microns in the copy paste. So that's the short dimension. And so this us that our detectors are still working pretty well after having been subjected to as part of the punishment that they'll see in the high luminosity LHC. With that, I'll go to my conclusions. The rich transitional Higgs bosons is an exciting place to explore, or still pushing down the error bars on the Higgs boson, especially when we can open up new channels to explore. There's strong motivations and interesting experimental features. We are well equipped for this exploration. The high luminosity LHC grades are well underway, and we are planning. I think it's time to address it in this talk, but we're planning now for the next generation of colliders. And I think extent will lead the way for us for the next few decades. Thank you.
So let's open up questions. Anyone ask a question, you'll need to repeat it.
Sure.
I mean, I know the history, but thinking of energy, luminosity, we always see a lot of guidance theoretically. If nothing is seen in the next handful of years, how does one get guidance about this next collider?
So you have to try to it was a long one.
Thank you for the reminder. I think the question was, we always had guidance for what kind of mass scale we needed to reach in the past with the standard model as a map. And now that we don't have specific expectations for what we need to look for, let's set the energy of the collider and really the technical limitations, as much as we can get to still have something we can build within a finite scale. Discussions for the next colliders, 100 TeV with Dream for a while, seeing numbers more like 33 TeV. The LEP for Hadron Collider. The LEP colliders are looking at more operating right around in the few hundreds of GeV, so enough to make lots of Higgs bosons and some of the parameter space above that. Compare lepton and hadron colliders. Hadron collider, you're colliding the opponents of the proton, so you pay a bit of a penalty compared to what sounds like much higher best for the center of mass energy for the collisions.
Yes. So this is a very naive. Universe infiltrate all your
So the question is, if the if the Higgs field symmetry had broken, if the electric symmetry had been broken in a different way, how would the world look different? And I'm probably the wrong person to answer that question.
Anyone else want to try to answer that?
Yeah, it's an excellent question.
If you're gonna answer, you have to talk about it. Or Anna maybe want to answer that, or some theorist. Okay, so Mike, you're gonna have to speak up and.
I'll take the microphone too. Yeah.
I don't know if we have a microphone.
I need to repeat the question too, right? Yeah. So the question is, if the Higgs, so if the symmetry being associated with the Higgs along a different axis, how the universe look different? And the answer actually is that it wouldn't. And it's a difference between breaking a gauge symmetry and breaking a global symmetry like a ferromagnet. Right? Because in a ferromagnet, you break a symmetry, spins point this way or they point that way. You can tell the difference. But in gauge theories, it's different, and it's still the case that even if your Higgs field points one way or another way, they're related by a gauge transformation, and so it turns out that there's actually no observable difference. So it's a kind of subtle thing about gauge symmetry breaking.
Repeat the question.
So the follow-up question is, if there's no observable difference, why do you have to put in the theory? Well, yeah, you're still right. You're still right. Having the phenomenon of spontaneous symmetry breaking is still there, gauge theories, and it's still in something, and it has consequences. But the direct symmetry breaking is, for this kind of weird reason, is not really one of them. Right, so I'll just repeat James's summary of the discussion. So we know it's broken, but we can't really talk about in which direction it's.
Anyone has one final question? Yes.
So that's actually the whole idea of having these fiction. Yeah. So if you have particles that are decaying faster, can't you just make a smaller detector? And that's actually kind of what we do with having the pixel detector close to the beam and being able to resolve things very precisely. And if we could build detectors that were infinitely precise and infinitely close to the beam, we'd be able to resolve more. Although some things decay instantaneously.
Maybe connected it, just try to respond in a different way. There are other detectors that give you finer resolution. Problem is that it's a trade-off between the resolution you're trying to achieve and how long it takes to read out the information. So if you're going to look at rare processes, you can't have things of spectacular resolution because you just know how to select out the right events. Okay, so I'd like to thank the speaker once again.
Thank you for your attention.
In person.
Yes, thank you. This was so great to give a talk to real to people in person.